Welcome to PanEuro Group and our review of geothermal energy.
The global energy system is currently caught in a strange paradox. We are building massive amounts of coal power capacity that we barely use, while simultaneously failing to retire the coal plants we can. This creates an expanding inventory of stranded thermal capital, fully functional coal plants that sit largely idle, maintained only as an expensive form of grid insurance. When developers try to repurpose these massive industrial sites for clean energy, their instinct is to look straight down. They want to find the hottest possible rock layers to build high-yield geothermal power plants. That approach works backward. By prioritizing the geological heat resource over the existing surface infrastructure, developers consistently end up with technically fascinating sites that are commercially undevelopable. Coal is a terrible conductor. Where thick layers of it exist underground, they act like a thermal blanket, insulating the earth and trapping heat in the rock below. This effect can artificially boost the local geothermal gradient by roughly 30%. But that insulation comes with a catch. Because the coal masks the heat deep underground, surface sensors read a negative heat flow anomaly. Traditional geothermal prospecting methods look for surface heat, so they systematically pass right over these prime basins. Finding that trapped heat is only half the battle. The absolute binding constraint for geothermal extraction is permeability. Subsurface heat is useless if you don't have water circulating through the rock to carry it up to the surface. When developers drill deep into these sub-coal sedimentary rock layers, they reliably hit the high temperatures they modeled. However, the sandstone formations they find are often incredibly dense and dry. They find the heat, but no flow. The result is millions of dollars spent discovering a resource that physically cannot be extracted. The most successful developers invert this process entirely. They don't start with the geology, they start on the surface. A retired coal complex leaves behind a massive bundle of hard assets. We're talking about permitted brownfield land, water rights, and crucially, multi-million-dollar high-voltage grid interconnections. To figure out if a site is viable, developers use a strict 4-gate screening process. Gate 1 requires an anchor demand load, like a dense residential neighborhood or a facility needing industrial process heat, within 5 kilometers of the plant. Gate 2 evaluates the retained connection assets. To move energy to that demand, the site needs a live grid interconnection, or ideally a retained district heating pipe network already in the ground. If a site lacks a local customer base, or the pipes and wires to reach them, it gets crossed off the list immediately. It does not matter how hot the underlying geology might be. If the site passes those surface checks, Gate 3 evaluates the subsurface target. Instead of chasing deep, dry rock, the most reliable target, known as Play A, focuses on shallow, flooded, abandoned mine workings. These mine voids are already filled with circulating water, naturally heated to around 15 degrees Celsius. Operators pump this water to the surface and use industrial heat pumps to compress and upgrade it to roughly 80 degrees, pushing it directly into district heating systems. This chart illustrates the reliability of the mine water model. For boreholes targeting mine voids at depths greater than 300 meters, operators are seeing a proven 97% success rate. The Gateshead scheme in the UK proves the model works at scale. Today, hundreds of homes, an arts center, and a college are entirely heated by water drawn from 200-year-old flooded coal seams. By combining existing surface assets with confirmed underground water flow, Play A successfully transforms geothermal energy from a high-risk geological gamble into a highly predictable, bankable infrastructure project. The flooded mine voids provide a specific, vital function. They operate as massive thermal batteries. When the macrogrid produces a huge surplus of wind and solar power, electricity prices drop. Operators can use that cheap excess energy to run their heat pumps at maximum capacity, effectively storing that energy in the water system. Then, when the sun sets, the wind dies down, and the grid is under severe stress, the geothermal plant can dial back its power consumption entirely, coasting on the thermal energy it already stored up. Providing this exact type of flexibility to a heavily renewable power grid is incredibly valuable. Within the next decade, the revenue generated from these grid balancing services is projected to dwarf standard heat sales. Ultimately, these defunct coal plants derive their value from the infrastructure bundle, the pipes and wires that allow them to function as the massive thermal batteries a renewable heavy grid requires.
For more insights to global energy, please contact PanEuro at paneuro.capital.com.